So welcome back. We've been building up to defining a generalization of Hamiltonian mechanics for a couple of lectures now. We have one final technical point to discuss before we can get to this promised generalization. That's the interior product. So this is an operation which takes a k-form and a vector field and produces a k-1 form. So we have some manifold M, some k-form omega, and some vector field x. Then we're going to introduce this operation of the interior product, which we'll denote with an I subscript x, and it takes a k-form, depends on this vector field x, and gives you in return a k-1 form. That's the interior product, and it's defined as so the result of applying this interior product to a k-form is a k-1 form, and if you stick k-1 vectors in here, because remember a k-1 form eats k-1 vectors, gives you a number. So what is the number? Well, the number is defined to be what you get if you put in x in the first argument of omega, and the remaining places you put those k-1 vectors, x1 through to xk-1. This is it's an operation. You can define it. And we're going to see that it's a very useful operation. You want to define it when you try and build a generalization of Hamilton mechanics. Because if you don't define it, then it'll be somehow forced on you anyway. Let's write it out in components so that we can actually do some calculations with this thing here. And then we'll derive some properties of this IX operation. We'll see that it has some quite remarkable properties. And then we'll be able to get to our topic of this, the main topic of this course. So if we have a k-form omega, then we can always write it in components, right? That's in some chart. If you had some k-form, let u phi be a chart with coordinates x mu, then you can always express omega as a linear combination of these bases, of the wedge products of these basis 1 forms here. It's a matter of convention if you put this 1 over k factorial here or not. Just rescales these coefficients here. And in order for this to be a k-form, you need that these coefficients here are in fact fully anti-symmetric under exchange of these subscripts. So we covered this when we discussed k-forms. And what we're going to do is take this formula, look at this definition here, and try and come up with a formula in terms of components for IX. So IX omega has to be expressible in terms of components. by convention, we pull out the k minus 1 factorial. This is a k minus 1 form on the manifold. Has to be expressible in components. Let's find out what those components are. Well, if you stare hard enough at that definition there, I think I used 2 in the notes. Yeah. So if you stare hard enough at the formula here, star, let's call this star, this definition, you should conclude that when you express I x omega in components that you get this formula here. And we'll make this a little exercise just to think it through. And of course we've got a repeated index here, so there's a sum over mu and mu2 all the way up to mu k. So if you forget these basis things here, just look at how these things are defined in terms of components. You just take a tensor omega with k indices, another tensor with 1 index, and you contract over the repeated index to get the coefficients in the new k form, k minus 1 form. Now, because these things are fully antisymmetric, if I exchange 2 of these subscripts, the new coefficients are negative of the original coefficients, then we can exploit that antisymmetry to get another form for this expansion here, which in practice can be more or less useful. It's a kind of more symmetric representation for the same thing. So whenever you see something with a big hat on top, that means drop it. And in this expansion here, we see that we indeed have a k minus 1 form, so that works out. And it has this somewhat more symmetric representation here. So it's a little, well, it's a little exercise, belongs to the class of exercises where you think a bit and you already see the answer. Let's do an example so that we can get a better feeling for this interior product. take the manifold as just R3, Euclidean space. Let's take some example 2 forms. So we could take, for example, omega is dx1, dx2. And we could take for x the vector field ddx1. Let's find out what the interior product of E1 of omega is. Well, if we consult our formula up here, this one's probably the more useful one, then we see there's only one coefficient here that's non-zero, well, up to anti-symmetry, and you could track down like this, and you should get dx2. What did I write in here? Oh, yeah, that's what I had here. And let's try another one. dx1 wedge dx3, say. And let's choose now for our vector field x ddx3. Just to highlight the anti-symmetry of the 2 forms here. So if we do the internal product of omega with x, then there's a couple of ways to work this form. You can just go over here and consult that formula here. The way that somehow works better for me is I think about moving dx3 past dx1, picking up a minus sign, and then I can deploy this first formula here that I can remember pretty well. So I'll show you what I mean. It's minus dx3 wedge dx1. And then you can put the vector field in the first argument, and then you end up with minus dx1. That's my preferred way of doing these calculations. Of course, if you like other definitions, then by all means work from the other definitions. It's always good to have more than one way of working with a thing, because what looks easy in one frame of reference can look complicated in another, and vice versa. I'll take an aside now to discuss a pictorial representation of these kinds of manipulations. So in differential geometry and symplectic geometry, you have to do multilinear algebra here and there. For example, here we're doing multilinear algebra. We're contracting tensors with numbers of indices. Usually it's kind of manageable. You only have to deal with things with, say, 4 indices or something like that. But occasionally, you have objects which have multiple tensor factors, and things get a bit hard to keep track of as you go through the manipulations. So there's a pictorial representation that you can use that can be helpful. Now this Formalism's been reinvented dozens and dozens of times and rediscovered. One of the earliest references that I'm aware of is due to Penrose. And the idea is to represent tensors, or in particular the components of a tensor, with a diagram. And then the operations of contraction you can also represent diagrammatically. And then when you depict some multilinear operations in multilinear algebra using these diagrams, then it becomes very rapid or very easy to see what objects you get out at the end are, instead of writing things out in components. So I'm just going to define this stuff by example. This is just one way you could build up this formalism. You can have a lot of fun building up tensor network diagram formalisms for yourself. As I said, they've been reinvented countless times. So I'll just do it by example. Okay. So we represent vectors with balls and sticks. The ball represents the vector. There's an index associated with the leg here, j. What does this mean? Well, this is the vector v superscript j d d xj in components. So in this diagram here, j takes the values, say, 1 to n. We're on an n-dimensional manifold. If you input a j into this picture, then this picture here is meant to be the number v1, for example. Except I'm going to change this diagram a bit. And we'll change this diagram even a bit more in a second. So this object here is meant to represent a vector. So a ball with one leg, each leg stands for an index, ball stands for tensor. In this case, the tensor is a vector. So the tensor, an object which is in the tensor product of a vector space with itself is a ball with two legs. And we always put vector legs going to the left. Well, yeah, go from right to left, let's see. That's arbitrary. Now we also have a diagrammatic representation of one forms and two forms, and in general any element of a dual vector space. So an element of the dual space is also going to be a blob with a leg, ball with a leg. But now we draw them from left to right. So one of the most important operations that makes this diagrammatic calculus work out is contraction. Which is represented by joining the legs. So you can imagine now how to build or to generalize this calculus. Suppose we have a mixed tensor. Let's draw a mixed tensor. That has to have two legs, one for each possible tensor factor. We have one going to the right and one going to the left. And then you can see that you can build quite complicated objects diagrammatically, and these represent tensors, and you can contract these tensors with each other to build other tensors. Actually building up a kind of symmetric monoidal category here in fancy language, but in very, very pedestrian language, we're just drawing pictures we're representing objects of mixed tensors, we're representing them via pictures. Now, to be a K-form, there's an additional constraint, right? So a K-form, according to this sort of way of doing things, is an object with K legs like this. But it's not just any tensor with K legs. There's a condition for this to be a K form, and that is that it's antisymmetric under exchange of any legs. So there's an equation that you can draw in diagrams for that. So exchange in diagrams very nicely corresponds to exchanging legs like this. Now this looks like a braiding, like I've drawn one leg over the top of the other, like that's different from if I'd drawn it under. But this is not meant to mean that this is a braiding. So this is really just I'm exchanging these two legs. That's what that diagram there means. So I'll write that up here. So if I just don't want the legs to get confused, right? If you like this as trivial braiding. So the equation that this guy fulfills is that that's minus that for all possible transpositions here. I'll do another one that shows it a bit more dramatically, perhaps. case of a 4 form. And now in this diagrammatic calculus, we can see what the interior product is doing. The interior product takes a k-form and a vector x and produces a k-1 form. How does it do it? Well, you take your k-form, put x in there, and you're left with k-1 form. That's the interior product in tensor network diagrams. You can have a lot of fun doing more things like this. This formalism becomes a bit more useful in Riemannian geometry, where we have to deal with 4-index tensors, but even here it can be sort of enlightening to think, what are these operations doing in terms of diagrams? The tensor product, for example, just sticks blobs together. I don't think I drew that yet. So if you have a vector field, a one form and another one form, then the tensor product just sticks the diagrams like this together, but that's no longer a 2 form. Remember, we had to anti-symmetrize. So, well, I'll do it for vectors first. That's the diagram for V tensor W. But 1 forms and 2 forms are different. We have to anti-symmetrize. So there, if you have omega and you have omega prime, well, that is indeed the tensor product of 2 1 forms, but that's not a form anymore. You need to anti-symmetrize, and that's an object which takes 2 forms and produces a 2 form. And an anti-symmetrizer is a 4 box. It's a box with 4 legs, and we'll just write it as P minus like that, and that's the anti-symmetrizer box. So that's the wedge product right there. Wedge in tensor network diagrams takes 2 forms, anti-symmetrizes to give you a properly anti-symmetric object. A question?
Yeah. How I'm able to differentiate these K1 forms and the K form, or arbitrary element of the K tensor dual with this K form. So there's no pictographic difference.
There's no pictographic difference between K single 1 forms and 1 K form. Not really. No, you have to reveal that structure underneath. So if you really have the wedge of 2 1 forms, you'd have to represent it like this to make that clear. Otherwise, I mean, if you just sort of blob together this diagram, I mean, you have this, right, on wedge. That's clearly a correct representation of this thing here. But to express this fact more concretely in diagrams, you should put in the anti-symmetrizer box as itself a mixed tensor from 2 to 2. So this language can be useful. You might find it helpful in this course to occasionally represent what we're doing in blobs, boxes with legs. Or you might not. It's up to you. Now, this diagrams calculus is really only useful for the multilinear algebra that you have to do. The analytic structure where you have to do derivatives and so on doesn't fit so nicely with this kind of calculus. It's not impossible. It's just beware that this does the multilinear algebra at a point on the manifold. The actual differentiable structure is a whole extra level of structure that's not so well represented with diagrams. But, you know, as we go through the course, maybe we'll see cases where that's still somewhat possible. yeah, I guess we could just do the exterior derivative to see what that looks like in diagrams. So if you have just a blob with no legs, that's a function on the manifold. Then the exterior derivative is an operation on diagrams that produces new diagrams. We have a one form omega, then D on that diagram produces a new two form like that, and so on. So it's possible to represent these operations diagrammatically, but there'll be a point of diminishing returns where this diagrammatic calculus becomes less useful. Now I want to show you a really neat formula, super cool formula, that relates the exterior derivative, the interior product, and the Lie derivative. Three separate things. So let omega be a one form. I'm only going to prove this for the one form case. You can do the k form case yourself. So in coords, so suppose we have a one form, we have a vector field x. Now, let's do some calculations with interior products and exterior derivatives. So the interior product of x with omega, if we look at the diagrams here, we can already see that that's going to be something simple. Where did I draw the, here it is. So we have a one form and the interior product of a vector with a one form. Well, that you just contract the vector with the one form, so you should get a number. Indeed we do. We just get the number omega mu x mu. Easy peasy, right? So let's do something else. Let's take the exterior derivative of that. So what? Well, what happens if we did it the other way around? Suppose instead we'd taken the exterior derivative of omega and then the interior product. Rats, raise the wrong board. Well, we'd also get a one form if we took first the exterior derivative and then the interior product. So we have two ways of getting a one form from a vector field and a one form. First interior, then exterior, or then exterior, then interior. So exterior product builds up a K form, and interior product pulls down a K form. And if you do these operations in reverse order, there's no particular reason to think you'll get the same answer. See what answer we get. do things the other way around. Okay, that's the result of taking an exterior derivative. You just partially differentiate with respect to the coordinates and then wedge on that basis 1 form there. And now we take the interior product with x. So in diagrams, I guess we went from omega to one with 2 legs. And then we're going to interior product on x. It's my pictorial representation for what we're doing here. And over here we had omega x. And we're going to see that we get a very neat difference. There's something very, very cool about what comes out of this. So I'll write out, this representation here isn't the best one for doing the interior product. So I'll write out an equivalent representation just using the anti-symmetry. It's of course the same thing. But now we have it in components. There's a nice formula for the interior product. So there we've got the coefficients with respect to these coordinate 1 forms. We've written them in this more symmetric form there. And then we've just applied the definition of the interior product there. And what we get out at the end is something that should be sort of pretty familiar to you from the last lecture. Yeah.
I don't quite understand the second step. Why do we use this notation to expand it and then to put it back in the form of the first line? We just rename the derivative to 1/2 times the matrix or what?
That's true. Yeah. You could have skipped the second line. The question is, why do the second line? Well, you don't have to. That's true.
And the indices should be swapped in the second line if the rightmost expression.
Oh yeah, I guess so. Wait on, what? Yeah, right.
Because in this way it's 0.
Yeah, otherwise it's 0, yeah. Yeah, there you go. So the purpose of the second line is to show what the components omega prime mu nu actually are. So there's d mu omega nu minus d nu omega mu. So if you want a purpose for the second line, it's that. Okay, that starts to look kind of familiar from previous week. So now what we're going to do is compare this thing and this thing up there by just adding them up and see what we get. And we're going to get something rather interesting indeed. So if we've done these operations and then we sum them up, then we get something very, very suggestive. So if you now use the product rule for the derivative there on the right-hand side, you see that one of those terms vanishes. So we get two terms here from the product rule, d nu x mu omega mu and x mu d nu omega mu. So that term vanishes. But this thing here, well, that has a name. We've seen that before in the previous lecture. It's the Lie derivative of omega. Actually, this is a clue for a more general result, one that you'll actually prove by yourselves as an exercise, although I mean it's in any good textbook if you're super lazy. It's actually true in general that on K-forms, dix plus ixd is in fact the Lie derivative. So we have a way to connect these operations of exterior derivative, interior product, and Lie derivative. Such as this is a super useful formula, use it a lot. And I'll leave this proof to you as an exercise. I did it myself in terms of components. It's just a bit tedious. All right, now I'm going to do sort of some more exercise, but I'll actually argue the proofs in terms of diagrams in some of these examples. So if we have two vector fields, and some K-form, You can start asking questions like, what happens if I do two interior products, or an interior and exterior, or Lie derivatives, blah, blah, blah. And you can combine all these operations and come up with a couple of rather interesting consequences. One of them is, for example, that if you take the interior product of a K-form with respect to the commutator of two vector fields, that has the following expression. That one's pretty easy if you just substitute in the definitions. I think for that omega has to be a one form. Yeah, a one form, right? In this example, no, this is okay. So 2 the interior product has a nice Leibniz-like property, or maybe we should call this an anti-Leibniz property. This one we can do a diagram of this just to see what on earth's going on. So that's the left-hand side. We take the wedge product of omega and nu, use the anti-symmetrizer box to make it a K form, a K plus L form. And then we interior product with respect to a vector like that. Now that's equal to minus that, equal to plus that, equal to minus that, and so on, where this x can be anywhere along this line here. L legs there, K minus 1 legs there, minus plus minus 1 to the K So that's not a proof, that's a representation of the left-hand side and the right-hand side. You can convert this to a proof if you like by thinking, how does x pass through the anti-symmetrizer box? And then you'll have the answer. Yeah.
You said this is okay for K forms. How's it to be understood? X acting on.
Well, X is just a partial derivative operator.
Yes, and on a K
On
form.
components, that makes sense.
Also, it's on the component.
It's on the level of components, yeah. Okay, another exercise. This one is also rather interesting. The interior product twice is 0, so it's nilpotent. So diagrammatically, this one's pretty easy to show. So if you do the interior product twice on a K-form, then that looks like that in tensor network diagrams. But because this equals that minus we're already done there, that's got to be 0. So it's got many of the similar properties of the exterior derivative, this Ix. But it's definitely not an exterior derivative. Now, a consequence of these exercises and this formula here is that the interior product commutes with the Lie derivative in the same direction. When you take these interior product and the Lie derivative in this along the same vector field. So I mean, that's an exercise, but it's, I hope that you won't find that too challenging. Take a look at this thing here. Apply Ix to the left-hand side. So Ix comes along here. You've got Ix d Ix plus Ix squared, so that's 0. Now apply Ix to the right-hand side. You got Ix d Ix, 0. So I've already done the exercise for you. And that's about all the formalism we need to get into Hamilton dynamics, or an analog of Hamiltonian dynamics for symplectic manifolds. So if you look at what you do in Hamilton mechanics, you stare at it hard enough and you try and translate all the operations you do into the language of Lie derivatives, interior products, and so on, then you'll arrive at some definitions. So I'm going to give it to you backwards. Instead of starting with Hamiltonian mechanics and then working out how to express each of the things we do in Hamiltonian mechanics in terms of these operations, I'm just going to straight out show you what the answer is, and then we'll derive Hamiltonian mechanics as a special case. So then you'll see what we're doing is a huge generalization of Hamiltonian mechanics. So to get started, we need a symplectic manifold. And we're going to need a function on this symplectic manifold, just some old function that for every point in the symplectic manifold, it gives you a number, a real number. And I've written it very suggestively as h. So given any function and a symplectic manifold, there's a canonical way to get a vector field from that function. So it doesn't usually happen, right? If you have a manifold and you have a function on the manifold, there's no canonical way to get a vector field from that function. You can get a one form from a function, easy, just hit it with the exterior derivative. But getting a vector field from a function, that tends to need extra data. Usually in Riemannian geometry, we have the data of the metric, so we can get the one form and convert it into a vector that way. Here, we also have a magical thing that takes one forms and gives us vector fields, and that is the symplectic form omega. So dh, that's a one form. Easy, that's good, right? And here comes the beautiful bit. Since this closed two-form omega is non-degenerate, there's a new unique vector field which we'll call xh. Such that if you interior, x, product that vector into our symplectic, our two form, then we get dh. So let's follow the logic from right to left. dh is a one form canonically associated with a function. And then we wonder, is there a vector field which gives dh as a one form? And the answer is yes, there's a unique such one. Let's call it x of h. So in components, well, not even in components, we're defining x of h by this formula here. So you stick x of h in the first argument of the symplectic form omega, and then you put an arbitrary vector in the second argument, and that vector field x of h has to satisfy this equation for all such vectors. And there is such a one because omega is non-degenerate. So now we have a vector field. We started with a function, now we have a vector field. Vector fields are good because vector fields can be integrated. They can be integrated, they give us a flow on the manifold, especially if the manifold's compact, then we got that flow exists for all time. So given a function, we now have a whole bunch of diffeomorphisms of our symplectic manifold coming from that function. Now why h? Well, h is going to be the Hamiltonian. This vector field here will be the flow generated by Hamilton's equations on phase space. That's what it all reduces to. But this is much more general. So integrate that vector field x of h, and suppose either M is compact or xh is complete, i.e. that's just like saying, in the non-compact case, let's suppose the flow exists for all time. So suppose either of these two conditions, then we have this flow coming from this vector field, which in turn comes from this function h. So we know they're diffeomorphisms. Turns out they're much more. And so we have, of course, that sigma naught equals the identity. And if you differentiate sigma t, you get x of h. So let's now observe something much more striking about this flow. It's not just any old flow. If you pull back the 2 form under this flow, it's preserved by the flow. It's actually invariant. That is much more striking. So we're actually in a position to prove this proposition. I don't have to wave my hands and say physically it feels correct. Let's study it for the harmonic oscillator and believe it. We don't have to do that. We can actually prove it. And it's far simpler than most proofs, which tells us that the definitions are on the right track. When striking results have simple proofs, it means that you've probably got your definitions well crafted and in a good state. So let's look at this thing here. We're going to differentiate. The trick we're going to use to prove this is we're going to differentiate left-hand side and right-hand side and show that it vanishes, and then we're done. And then because we know it's sigma naught, we know when t is naught, that omega equals, the left-hand side equals the right-hand side. So we show that the change that this thing is constant. Now, this has another name. All right, we've seen that thing before in the previous lecture. That's just the Lie derivative. Now we'll see that all that hard work we just did in looking at interior and exterior products was worth the effort. So we have this lovely formula for the Lie derivative on a K-form. dIxh plus Ixhd on omega. Look a bit like stars. Let's make them H's. Let's look at this now. So the interior product of the vector field xh on omega, well, the very definition of that is that it's dH. So we've got d of h plus, and here's the other bit that shows you that we're absolutely on the right track, d omega. Now we have a little exercise that you did a couple of lectures ago. dd is 0, yes? Oh, but look at this. The very definition of symplectic manifold includes in it that omega is closed, or in other words, it's equal to 0. So this is 0. So see how, for this proof, we use two facts. We use the closedness of omega, and we used the definition of the vector field xh. Yes, a question?
Yes, from the second step, I can follow from yes to there.
To here, to there?
Yes.
So that we did this in the end of the previous lecture.
But
So the push.
The derivative would be this expression there, evaluated at t equals 0, right?
Oh, but it works for all t, right?
But then still we.
This is just another form. Just do it from t to t plus epsilon.
Okay, but then this x would be included in L, right? Xt, like the pullback. Or am I mistaken?
So it's let me write out this then. Let's just use the definition of the derivative. So exp t plus epsilon xh star minus exp t xh star divided by epsilon. That's the derivative. And then we're free to pull off the xh from either side. Well, e to the epsilon xh minus identity and there we go. That's just the Lie derivative. So, conclusion. For all functions on the symplectic manifold M, the sigma t is a symplectomorphism. So if you ever want a symplectomorphism, just pick a random function on the manifold, and then you'll get one. And to honor the role of Hamilton in all of this story, we're going to give his name to these things. H is the Hamiltonian. And XH the Hamiltonian vector field. Now we've got a lot of stuff that we can put together. So Hamilton's equations, as formulated probably in your physics course, pertain to Euclidean space, phase space, which is just two copies of Euclidean space, and you have the infrastructure of Hamilton's equations. Here we've now generalized phase space far beyond its original formulation in terms of just Euclidean space to symplectic manifolds. So symplectic manifolds are the generalization of phase space. That's the way to think about them. And all phase spaces, as we'll see in the next lecture, are symplectic manifolds pretty much straight away. But there's plenty more, right? There's loads of symplectic manifolds. In particular, take your favorite manifold, work out its cotangent bundle, and we know that's a symplectic manifold. So we have a ready supply of examples of Hamilton-like systems associated with a vast variety of different manifolds. Let's do some examples. Well, let's do a Hamilton example just to see how, in this new language, how things look. So suppose we take as our manifold R2 as our base manifold. R2 is indeed phase space for a single degree of freedom for a particle on the line. Right? It's R cross R. And let's take just this function that everyone knows, right? A half q squared plus p squared. So the coordinates of this manifold are qp's. Or do I do p, qp's? So that's I hope, a fairly familiar function on this phase space. And then let's work out d of h. That's what we need to work out our vector field here. We need to work out the one form associated with this function. And we get q dq plus p dp. Okay, it's perhaps not something that you're used to working out, but you can do it. And let's work out the vector field corresponding to this one form under the symplectic form. Oh, I didn't tell you what the symplectic form was. dq wedge dp. Now we need to work out x of h. That requires that we find some vector field that when we interior product it into this two form here, we get this one form. This is somehow the trickiest part of the whole thing. There's an implicit indirection in the definition of the vector field x of h that sort of forces you to do it by trial and error. I mean, of course, we have formulas for these things. So if you interior product this vector field here into this symplectic 2 form here, you should get that one form. So let's just check. If I interior product this vector field here into the symplectic form, I get dp, ddp, dp, and indeed I do, right? So indeed one term matches up when I take think about the interior product of this vector field into this symplectic form here. So we get pdp, and we also get q. Well, you put p into here, but it's in the second argument. You get a minus sign, so minus dq. So you get q minus dq, but that's just plus. So we get that there. And you can integrate this vector field you know it's the harmonic oscillator, you know what the flow already looks like. If you have some point in phase space, qp, under this vector field here, the flow is cos of minus t q sine of minus t p. Let's see this machinery now at work. See how easily it delivers us generalizations. That aren't no longer coming from Hamilton mechanics, but which share all the same features. So our second favorite example after the cotangent bundle for real Euclidean space is the two-sphere. Very interesting symplectic manifold in its own right. So we'll consider the two-sphere embedded in R2. And we'll call the z-axis h. So it's now the h-axis. H stands for height, and also Hamiltonian. So to specify a point on the sphere, you need two coordinates here. Angle, which I believe I've called theta, yep, and height. So in the coordinate system given by angle and height, so that's basically a chart for the whole sphere except at the poles. In these angle height coordinates, we're going to choose the following function on the two-sphere. H is just the height. So the thing that's going to be generating, capital H is just the height. I.e., if you evaluate it on angle height coordinates, you just get the second argument coming out. And we're also going to need a two form to make this a symplectic manifold. And we're going to use this particular 2 form. It's closed, so you can check. Of the many 2 forms we could have put on the sphere, this is the one we're going to choose. And then that leads to the following vector field, x of h equals d d theta. And we have finally that the flow generated by that vector field is as easy as it can get. Namely, the point just rotates around the sphere. So I haven't quite shown that this is a satisfactory generalization of Hamilton mechanics, because there's a couple of features you expect from Hamiltonian mechanics in order for it to be a model of mechanics. So perhaps the most important property of Hamiltonian mechanics is that energy is conserved. Right? There's a symmetry under time translation, and the generator of time translations is the Hamiltonian, and the conserved quantity corresponding to that generator is the energy. So it's a really fundamental fact about classical mechanics. And I'll make that comment now. So we're going to prove that the energy function is preserved under dynamics generated by these Hamiltonian vector fields. So if x of h is a Hamiltonian vector field, then we can take the Lie derivative with respect to h of that function. So h is a function. You can take the Lie derivative of a function. It's just equal to the vector field applied to the function. Or we can use that lovely formula to express it as the interior product of dh with respect to xh. But let's use the definition of dh as the interior product of the symplectic 2 form like that. But now we know that this vanishes like that. So the Lie derivative of h is 0. And as a consequence, we're going to learn that the level sets of h are left invariant. So if you start at some initial point on the symplectic manifold and compute the energy of that point, it's a number, and then you wait for some time and compute the energy after the vector field has operated for some time, compute the energy, you get that that's actually equal to the original energy. So energy is conserved. It's a consequence of this observation here.
So is this same argument as before when I asked that this is a very local expression, this L, and then you can just globalize it because it's like the infinitesimal version, or?
Yes. Yeah. You can globalize it with this infinitesimal expression. All right. Then I think we'll stop there. Energy conservation is as good a law to end on as any. Okay. In the next lecture, we're going to look at types of vector fields, classify vector fields according to whether they're Hamiltonian or whether they're a slightly more general thing called symplectic vector fields. And we're going to look at Hamiltonian mechanics, then we're going to get on to Lie groups. So the objective, so for the last part of this course, is to generalize Hamiltonian mechanics even further. So we're going to go for the most craziest generalization imaginable. You can think of Hamilton mechanics as the group R, the real line, acting on a manifold, right? What does it do? You choose a time, and then a Hamilton vector field gives you a flow, and it tells you what all the points look like after some time t. Well, how we're going to generalize this is we're going to replace time with a group, a Lie group. So we're going to be able to deal with like multiple times, or even times that don't commute. So this mind-bending generalization turns out to be extremely useful for loads and loads of applications in physics. And at the end of this course, I hope to at least show you one or two of those crazy generalizations and what they look like physically. All right, but for now, I'm done. Thank you very much.